All right, hey guys, here is our lesson 6 group problems. For number 1, there's a probability of 1 in 150,000. You can see here. So you have to take the square root of that to find Q, and that comes out to be 0.0026. All right, and then for B, you have to do like the reciprocal of that. So you take 1 minus this to get the probability of our P, and that's 0.9974, or in other words, the dominant in the recessive. Then for C, you go into there, it's asking for the P squared value. So you take that squared from B and you get 0.9948. And then for D, it's asking for the heterozygous possibility. So you take 2 times your answer from A times your answer times of B, and that is equal to 0.0052, and that's your heterozygous.
Oh, we can right here.
All right, we're coming over here for number 2.
Number 2 is right here.
Oh, that's right. So for A, the first one was Q, while the next one was 2PQ.
For B, it's going to be P. You start to see that is a dominant disorder, so that's why it's P.
And then for C, it's Q.
And then D, we chose R because it's the most recessive of them.
And then for E, you get P squared for the first one, and then 2PQ for the next part.
There's 2 parts.
Or it's P squared and 2PQ.
Okay. So F is sickle cell. Sickle cell is the result of S and then P. That's in the slides.
G is monomorphism or monomorphic.
And then H is Denny's. It's also in the slides as another name for local population.
And then I is major histocompatibility complex. It's also in the slides.
All right, so 3, we might have done this differently because of the order of the questions. I did B first. So I did 1 over 6,000, square rooted that to get 0.01291. Then I used that number to answer A by minusing that by 1, which equals 0.98709. Now, if you did it where you did it this way, you did 4, so you did the square root of 4,999 over 5,000. You'll get a different number, so my numbers are going to look a little bit different than yours if that's the way you did it. So I took those 2 values that I got up here, so these 2 values, and I times them together, also times them by 2, is to get the heterozygous number, which is 0.02549. Then I times that number by 5 million. That's right, okay. And I got 127,433.319. So your number will look different than mine because if you did it that way instead of the way I did it. So just bear in mind for that.
All right. Number 4 was a bit different, using all the chi-squared and stuff. So for part A, you're looking for the R2 gene. And so you take, since you're doing alleles, it's not going to be the number that it shows in the problem. So you have to kind of solve for that number. So that's 2 times 135, because there's 135 homozygous dominant, plus 44 from the heterozygous ones, and divide by that by the total number, which was supposed to be 180, wasn't it? Oh, 380, no, sorry. 380. Because you have to multiply it by 2, the total number of people by 2. And that comes out to be 0.82632, and that'll be your P. Then you go to your R3, which you also had to calculate. Take 44 from the heterozygous, plus 2 times the homozygous recessive, which was 11, and divide that by 380, and you get 0.17368. and that's your Q value. So for B, we're doing a chi-squared test. So we have to find a null hypothesis, and that's going to be that this is in Hardy-Weinberg equilibrium. That's what we're testing for. So now we have to take the values that we got from A and figure out what our theoretical amount per genotype is. So you get P squared, and that equals 0.6828. Multiply that by the total number of individuals in the population, which is 190. You get 129.732. And for the heterozygous, you get 2PQ, so that's 2 times your R2 or P over here times the Q value, which was 0.17368. And that comes out to be 0.28704 multiplied by the number of individuals, which is 190, is equals to 54.5376. And then your homozygous recessive, which is Q squared, is going to equal 0.03017. Multiply that by the number of individuals, which is 190, you get 5.7323. All right, and then you take those values as your actual, and you go into your chi-squared equation here, which is observed minus actual squared divided by actual. So you take 135 minus 129.732 from up here, square that, square the numerator, and we'll divide it by 129.732 again. And since you're summing everything, you're adding the heterozygous one. So you have 44 minus 54.5376. Square the numerator, divide it by 54.5376. Then you add 11 minus 5.7323. Square the numerator, divided by 5.7323. And that'll come out to be 7.0907. And looking at the chi-squared table, now looking into C, we see that there are 3 different possibilities. So you take the 3 minus 1, it's going to equal 2 degrees of freedom. So you look at the chi-squared value table, and 7.0907 is in the section where you reject your null hypothesis. And a few different reasons can happen for that. For Hardy-Weinberg equilibrium, it can be through immigration, like I put here, or it can be through natural selection, or there's 5 different reasons that it can happen.
Okay, so number 5. We're almost there, guys. We're almost done. Okay, so the numbers of the equilibrium, Hardy equilibrium, are given. So you'll just want to look on. Oh, it's not showing. We'll just look on the paper for those. So these two, you're gonna square them to get the number for the first one for the C chinchilla, the 2 chinchillas, and then for the C, B, and C, you'll do the PQ, the 2PQ equation, and you'll use that to get the number that you need. And then the CC is also the squaring again. And then for this one, you'll want to do the, to figure out how many in a population, you're going to do the 2QP equation to get the number for that, which you can see it is done up here as well. And then you'll times that by the population we're looking at, which so there'll be 150 in that population that will have CBC. For this one, the way the worded is CD, CB, or CDC. So it's looking for CD to be heterozygous, so those are the only 2 options. And so you'll do the 2QP for one of them and 2QP for the other, and then you plus those together to get the number you need, and times that by the population to get 920. And then you'll do that again for this one, for the 2 possibilities that she's looking for. And then you'll do those equations. One of these is going to be squared though, so you'll want to catch that because that's 2cc. And then you'll times that by 15,000 to get 3,112.5. And that's it.
Have fun.